Alright, in this short lesson we're going to look at these things that I call toolbox functions. Some textbooks are coming around and they're also starting to call them toolbox functions. What we mean by toolbox functions, it's going to be a function that is basic to math, that everyone would have one of these in their math quote-unquote toolbox. Okay, so we're going to start off with f of x equals x. It's a for all these toolbox functions that we'll look at in this lesson, we could build a table of values and plot all their points and see what their graphs look like. What we want to happen with toolbox functions is we want you to see what the underlying function is and immediately have a picture in your head of what the basic thing looks like, and then in the next lesson we'll do some changes, we'll do some transformations to it to see how that changes it. So here, f of x equals x is a great toolbox function. I could also write that as 1 times x plus 0. And the reason I write it so weird like that is so that you can see that all this is a linear function, mx plus b. It's in slope-intercept form. So I know that the y-intercept is 0. So it's going to cross at the origin, and it has slope of 1. So it's going over 1, up 1, over 1, up 1 the whole time. So the graph of f of x equals x is simply a straight line. It cuts the x and the y axis, cuts down the middle of the quadrants here, in quadrants 1 and 3. Its domain would be all real numbers. Its range, what it spits out, its outputs, are also all real numbers. Okay, so that's what all straight lines look like. If we do some well, I'm getting way ahead of myself, but like I said, in the next lesson, if we do some changes to it, all it's going to do is, move it up or down, left or right, depending on what these constants are, m and b. Okay, so let's go up in power and look at good old x squared as our next toolbox function. So again, if you need me to, just let me know, and we could build a table of values and you could confirm all that I'm drawing over here on the left. Which x squared, it's a quadratic. You probably haven't seen that yet. I'm checking the current textbook. My guess is it's coming up. Yeah. But I've said it, so I'll tell you. It's called a quadratic equation. Its graph is always this horseshoe graph that comes in and bounces at the origin. It's decreasing. It's coming down on the left, hits the origin, and then bounces back up to the right. Its domain, remember, there's only two ways to not be in the domain of a function. Cause division by 0 and have the square root or the fourth root of a negative number. Those even roots of negatives. So the domain here is all real numbers, because you can plug anything into x squared and you'll get a real number back. And its range is your outputs, y, are always greater than or equal to 0. Basic toolbox x squared. It's a nice horseshoe graph, bounces at the origin, goes back up here, increasing on this side. So it never, just x squared by itself is always greater than or equal to 0. It never has negative outputs. Continuing our power uppage. So the first one was x to the first, the second one was x squared, this one, the third one, x cubed. How logical of me. So, we have x cubed and its graph. Again, I could confirm all these by building a table of values. I'm not, because unless, again, you just need me to. I may do this one, but I doubt it. Here, this x cubed graph is this nice little S-curve, passes through the origin because 0 cubed is still 0. Its domain is all real numbers. Because, again, there's no division by the variable, there's no root of the variable. And the range in this case is also all real numbers. Every number that you could possibly pick on the y-axis, there's a corresponding piece of the graph. There's a point on the graph that has that output. So we get both positive and negative outputs here because we're cubing it. Like if you plug in negative 2 cubed, you're going to get negative 2 times negative 2 times negative 2. These first two become positive 4 times negative 2, so you get negative 8. So you're going to get negative answers when you plug in negative x's, and you'll get positive outputs when you plug in positive x's. Okay, so we'll stop with the powers there because it gets a little uglier, and more things could go on when we get higher powers. Hold on. The next toolbox function I want to talk about is absolute value of x. So we've seen the absolute value as a tool before when it was inside some of our equations. The graph of it as a function is this big V that bounces once again at 0, 0. But unlike x squared bounced at 0, 0. But it did it with a nice smooth turning point. The difference between x squared and the absolute value of x is that x squared, you would survive this turn if it was a roller coaster turn. If you had a roller coaster on this track, you come down and then go back up. Absolute value makes a 90-degree turn at the origin. So you're not surviving that one without a lot of whiplash. So that's a sharp turning point. Its domain, all real numbers. Its range, only non-negative numbers. Your outputs in this case are always greater than or equal to 0. Again, we made that point earlier with absolute value that was always had positive outputs. We're just now confirming that with a graph. Okay, so we've done x squared, x cubed, absolute value of x. Square root of x is the next basic function. So its graph, well, we can go backwards here and talk about its domain because it's the first one with a domain issue. We can only plug in positive numbers because the square root of x, in order to be a real number, we have to have a positive number underneath the square root. So it has to be the square root of some positive number. Because we can take the square roots of negatives, that's why we did the complex number section, but we don't graph them in college algebra or any undergraduate math that we teach here at LCU. So when it's an even root, the square root, the fourth root, the sixth root, the domain is always greater than or equal to 0. The range is similar to that. Y is always greater than or equal to 0. So when we graph this, we're only going to have to plug in positive x's, and we're only going to get positive y's as output. Okay? Now, we could plot points. I haven't yet, but 1 would be 1, or 0 would be 0, 1 would be 1, 4 would get you to 2, you got to go all the way up to 9 to reach a height of 3, 16 to 4, and so on, the nice numbers. We could plug in 3, but we get the square root of 3, which is 1.5. blah, blah, blah. And so it's not going to, any of those ugly square roots we'd have to enter into our calculator. And that's what we're trying to avoid, is these tables. We want to be able to, when someone says, hey, the graph of square root of x, it would be really nice and mature mathematically of us to just see this graph in our head. I'm losing. Okay, we've done x squared, x cubed, absolute value, square root. One more. I call it a toolbox function. F of x equals 1 over x. It's got a domain issue on all real numbers except 0. This function does not play with 0, because if you do, you get 1 over 0, and that's undefined. For my Bible majors out there, that's like the Garden of Eden. God told Adam and Eve, you can eat of any tree in the garden except that one. So this function can play with every number except that one. The range is, I can write it in two ways. The y's, the outputs will always be negative or positive. That's one way of writing it. Or you can simply say the range is all real numbers except y equals 0. This graph never crosses or touches the y-axis or the x-axis. It can't touch the y-axis because that would be x equals 0, and that's not in the domain. And it doesn't touch the x-axis because this fraction can never equal 0. The only way a fraction can equal 0 is if the numerator, the top, is 0, and this one can't be because it's 1. So if we were to plot points, we'd get the following graph. Let's change colors to make that a little easier to see. Let's go with green. The graph would be this little skateboard ramp here, and its mirror image down here in quadrant 3. You're going to start off really high, near positive infinity, because if your x's are really small, then this fraction is going to have a really big value. If you plug in 0.1 for x, then that whole fraction has a value of 10. If you plug in 100th, 0.01, then your whole fraction has a value of 100. So we're way up here. As our x's are smaller and smaller, our outputs get bigger and bigger. And then the opposite is true. As our x's get bigger, as we move out this direction in the x, the outputs are going to get smaller and smaller. The more people you have to share this dollar with, you're dividing 1, the more people you have to divide it among, the smaller each person gets. And then on the negative side, you just have negative. When you plug in negative x's, your whole fraction's negative. And so these negative inputs create negative outputs. So we have our toolbox functions. X, whose graph is a straight line through the origin. X squared, nice horseshoe graph. It's got an official name, which I will probably say it out of habit. It's called a parabola. The book hasn't told us that yet, but I just did. X cubed, nice little S graph coming through the origin. Absolute value of x, the v bouncing at the origin, square root of x, starts off the origin and grows slowly towards the right, and 1 over x, these two little quarter pipes for our skateboarders. So those are the toolbox functions. Those are what we do the majority, well, I wouldn't say majority, but that's what we do a lot of our math with. And so we're going to, in the next lesson, see what happens to these as we add numbers in different places. All right, I will see you next time. Bye.